I'm blind. You guys hadn't noticed that?
What?
I read it, we read it, you read it? Really? Wow. Yeah. Well, it's because before, when people need to get used to the objective, I would read it. Everybody would read it with me, and then everybody would read it by themselves. So, our objective for today can solve and graph quadratic equations. So, today we're going to start wrapping up the quadratic equations portion and moving into substituting values for imaginary numbers. So, hopefully all the practice that we did already is going to start kicking in. Yes? All right. So, quadratic equations. Freyer model. Get that in front of you. And I want you to write a definition. Do not look at your notes. Just a definition. See how you do with that. Copy and go. Give you some time. So hopefully you have something like that. Yes? Pretty close? All right. So yesterday we covered completing the square. Yes? And we did plenty of practice with that. And then we got to your favorite, which is quadratic formula. And then we did some of those. Yes? And then from there, we wrapped up with that. Well, today we're going to continue. And we're moving on to this. Write this down, please, on your Cornell notes. Common used equations and quadratics. Today we're going to apply to word problems or real situations the quadratic equation, solution type, and so on and so forth. But I'm going to give you two equations that are used the most often. Okay? And this is in regards to time, distance, and so on and so forth. The first one, I'm going to do this in blue. You should write it in blue also. It says, distance of fallen object in feet at time t in seconds. This first formula is the distance of a fallen object in feet at a t time in seconds. What is that formula? The formula is d of t equals 16t squared. d of t equals 16t squared. I hope if you look at it, one thing that is obvious is the letter D, which means what? Distance of the fallen object in t seconds. Now, on this side, we have t squared instead of x squared. Why don't we have x squared, Mr. Q? Because the t stands for time in seconds. So whenever we solve this, we usually solve for the letter t. Okay? The second most common used equation is one that involves height in feet. I'm doing this in green. At time t seconds, where h sub 0 is the initial height in feet. Once again, h sub 0 is the initial height. What does that look like, Mr. Q? H of t equals h sub 0 minus 16t squared. There's only two for right now. Those are the ones that we're going to use most often. So what do I need to worry about these two equations, Mr. Q? How to know which one I use? Well, if a word problem, look up to the screen, only gives you to solve for the time it takes to go through some distance, that means we only need to worry about substituting a value here for the distance that they give us. And then we solve for t, which is what? The seconds. All right, how about this one? This one has more to substitute. What does it have? H sub 0. What does that mean? The initial height of whatever they're talking about. They're talking about a building that's a certain height. That's the initial height. If they're talking about a boat of a certain type of height, that's the initial height. But then they're going to say, well, what about this one, Mr. Q? Yeah, that one is the new height, or whatever they want us to figure out after it gets to a certain height, after it gets to a certain height. But the original or initial height is what? H sub 0. Why H sub 0? Because that's starting from 0, or the 0 distance there. All right. So let's see one example. Here it goes, example 3. Write this down. If you drop a water balloon, how long does it take to fall 4 feet? Just copy that. If you drop a water balloon, how long does it take to fall 4 feet? Sorry? We are solving it, but for right now, just copy that, this part right here. If you drop a water balloon, how long does it take to fall 4 feet? So look at it. Does the problem give you a certain height? No. What does it give you? How long does it fall to 4 feet? So which equation do we use? The distance and time formula. So it's d of t equals 16t squared. So what distance do they give us to figure out? 4 feet. Where does that go? Right here. 4 equals 16t squared. Does that look familiar? Yeah. Now we just need to choose which method to use to solve it. We have 5 different methods now. Graphing, factoring, square roots, completing the square, and quadratic formula. Leo, which method do you want to use? We're going to use whichever Leo says. Square root. Let's do that. And that's a good choice because that's a very fast-paced process. So line down the equal sign. Square root means that we need to isolate x squared, but in this case, t squared. So what do I do here, everyone? Divide by 16, divide by 16. We're left with t squared on this one. That leaves us with 4 over 16. Now we can take the square root here, or we can simplify first. What do you guys want to do? Simplify. This is 1 over 4 equals t squared. And since we're using the square root method, what's our last step? Square root. So we take square root of this, square root of this cancels this. We're left with t 4 times. What is square root of 1? 1. What is square root of 4? 2. Now check this out. We usually do this, right? Plus, minus. However, tell your neighbor why we don't use that one. There's no such thing as negative time unless we start inventing time travel, right? So this is seconds. So let's answer the question. Now, some of you got points on the part A because on the word problems you didn't write a statement. That's 1 point. What is the question? How long does it take to fall? What is falling? The balloon. So you write the balloon takes half a second to fall 4 feet. 10 cubes. Pretty simple, yeah? Piece of cake. Does everybody notice that it didn't talk about height at all? That's why we use this formula, the first one. Okay, let's go to the next example. Example 3Q. Copy this one. It says, the rooftop of a 5-story building is 5 feet above the ground. What does above the ground mean? In what? Height. How long does it take the water balloon drop from the rooftop to pass by the 3rd-story window? 24 feet. What does 24 feet mean? The new height. They want us to figure out up to right there. When is it going to take? How long does it take to get to there? I'll give you some time. Copy that. If you want to sketch also the little diagram that they give us. Go. All right, so which formula do we use? The height one, because this one they give us a height here and a height here. So we use h of t equals h sub 0 minus 16 t squared. So that's where I'm going. So I want you to box this. Sub 0, which means initial height. So let's read the problem. The rooftop of a 5-story building is 50 feet above ground. What does 50 feet above ground mean? The initial height. So we substitute here 50 minus 16t squared equals. So if this is the initial height, let's continue reading. How long does it take the water balloon to be dropped from the rooftop by a third that passes by the 3rd-story window at 24 feet? What is 24 feet? The new height. Where does that go? Right there. So it goes over here as our constant, 24. What's that? No. This whole thing is what we need to compute. All right. So look at it. And Leo said, I like using square roots. Can we continue using square roots to solve that one? Yeah, let's do that. So therefore, we need to isolate t squared. So what do? Subtract 50, subtract 50. We're left with negative 26 equals negative 16 t squared. Next step. Divide by negative 16, divide by negative 16. We're left with 26 over 16 equals t squared. And our last step. We can simplify, but I'm going to do the square root because I notice here, notice what 16 is. Isn't that a perfect square? Yeah, so let's take the square root right here. So this cancels that. Do we need to write the plus minus? No. So therefore we're left with square root of 26 over 16. However, can we simplify a little bit more? Yes. We're left with square root of 26. And what is square root of 16? 4 equals t. However, here we encounter a slight problem. We need to answer this in words. How long does it take the balloon to drop? How long, which is in seconds? How many seconds is that? No. So, yeah, it takes square root of, no. So let's simplify this. Let's see. We can either rewrite it as 1/4 square root of 26, or think about it like this. What comes close to square root of 26? Square root of 25. So therefore, we're going to approximate for right now just to write our sentence. So what is square root of 25? 5 over 4. So what is 5 over 4? 1.25 approximately. However, we cannot write the 5 because is it square root of 25? It's a little bit more, so I'm just going to write 1.2 approximately t seconds. Now, we can go through the process and I can show you how to get the decimal equivalent, but we're not going to do that right now. That's not the purpose. I want to make sure that you understand how to use the formulas. Look at the process. Can you tell the difference between one problem and the other problem and how to use the formulas? Yeah, we got this, yes? We could have used it in the sense that if you manipulate this a little bit, but if we're using just the exact information they give us, basically we're using that. Okay? Now, really quick in passing, look up please, write your utensils down. Now, let me tell you, because some of you, like me, some of you are like me. I like to know where things come from, not just be given stuff to get and do stuff. That's why when I was a kid, I remember I used to open up the radios, my grandfather's radios, and break them and stuff, because I wanted to see like the speaker and all the components and stuff like that. So, don't you notice that both of these equations have 16? Yes. And that's pretty weird because it's in both equations. Well, this is related since it has to do with falling objects. It has to do with gravity. So those of you that took science, who went through gravity already? You guys cover that? Yes? Well, like I explained to my students at the middle school level, I remember just to get my basketball and I would say, okay guys, this is Earth. Yes? And then if I spin this on my finger and it stays put, There's gravity pulling it towards the center. That's why it stays on the finger. But that's if it spins. What happens if it stops spinning? It's going to fall. That's why Earth is spinning all the time. It's at an angle of 23.8 degrees. 23.8 degrees, and it keeps spinning. That's why, because if it was to stop or slow down, we would start going like this and start going into space. But no, we don't fall. That's why the Earth keeps spinning. We keep going towards the center of the Earth. That's why it stays in its axle. So what am I saying with that? There's forces that we don't see that are mathematically computed. Those forces, after they do the computation, who's heard of G-force before? Yeah, G-force, it's basically gravity force. G-force, when you get into that, they come up with a number which is 32 point and change. How much? 32 point and change. But that's when there's two directions pulling to it, right? But when the object falls, there is no two directions. There's only one direction. So therefore, instead of being 32, it's 16. And that's why they kind of like generalize it to 16, and that's where we get that. Does that make sense? All right. So, one direction. No. So, with that said, let me show you a third type of word problem that you're going to encounter that is very similar to the previous, but it's a little bit different. Don't copy this, just pay attention. It says, on the moon, the distance in feet that an object falls in seconds is modeled by the function dt equals 8/3 t squared. What do you guys notice on this one? That they actually give you what? The formula. So that means whenever you get to these problems, instead of using the formula that you know, either the distance or the height one, you use whatever they give you. So whatever they give me is d of t equals 8/3 t squared. But what do we know about this? That this is distance, isn't it? Do they give us a distance? No. 4 feet is the distance, so that goes right there. We substitute, and we solve. Do we know how to solve? Yes, we have 5 different methods, and so on and so forth. Okay? That's equally, yes, for gravity in the moon. All right, so, we go up to right there? Crank it up. Write this down. Imaginary numbers. Ha, 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 ha. Yeah? You know. All right, here we go. It says imaginary numbers. So pay attention to what I'm about to say. I'm going to write something in black. You don't have to copy that, but as soon as I write something in red or blue, copy that. So what I'm going to elaborate in black is stuff that we already know, we already saw. I'm just kind of trying to refresh your memory. Here we go. When we first started our school year, I started with real numbers. You guys remember this? And then with real numbers, I gave you examples, and then I gave you a non-example that looked like this. And then I said, tell your number why this is a non-example. Well, square root of negative 16. One number times itself gives me negative 16. There is none. Because 4 times 4 is positive 16. Negative 4 times negative 4 is positive 16. There is none that gives me negative 16. So I said, this is a special situation. This is what we call imaginary numbers because we can rewrite this like so. And I said, square root of 16 is 4, and whatever we have left here, we know it as I, which is imaginary. Are we there so far? From there, I said, so what can we conclude? I brought this back later on again in the warm-ups, and I said, what can we conclude here? Therefore, that I is what, everyone? Imaginary, but I know, but what does it represent? square root of -1. This you need to know. What does that mean? Write it down. This is something that you need to know. You need to always have it in mind. You need to remember it. I is square root of -1. All right. Now that we got that, let's go to the next. Let's say I say I times I. So basically I did this times itself. What does that mean? That means this times itself. Do you agree with that? Yes. What's another way of writing I times I? I to the second power. That means that if that's true for this, I can write this how? Square root of -1 to the second power. However, look at this part. Pay attention, please. Look at this. Who notices that there's a square here with a radical? What happens? This cancels that. So what are we saying? That square root of, I squared is -1. Write that down, please.
Why would we ever need I?
Very good question, Ethan, because we're about to get started with that. Bam! Let's go. Unite. All right. So what are the two things that we need to know? That I is square root of -1, and I squared is what? -I. Okay? All right. So I'm going to start slow. Not to to overwhelm you. So I'm going to start with what we've been doing on warm-up. So watch. Look up to the screen. Don't copy. Just pay attention. I've been giving you stuff that looks like this. Is that correct?
Yeah.
But what if I replace x's with i's? Are we there so far?
Okay.
What is I squared? -1 plus 5 times I. What is I? Square root of -1 plus 6. Can I simplify from there? Yes. This one with this one gives me 5, and I'm left with plus 5 square root of -1. Can I simplify this anymore? No, so I'm left with 5i. Copy that, please. Now I'm going to label this one example NJQ. Now, this one I'm just giving you like in advance because we're going to get to those, but I just wanted you to see how we're going to apply substitution. But right now we're going to do another exercise which involves doing operations with imaginary. Okay? Pretty simple, right?
Yeah.
Yeah, as long as we remember the values of I squared and I, we're good. All right, let's go to the next. On your screen, you have example 4. Copy that on your Cornell note, please. It says, square the following imaginary numbers and simplify. Square the following imaginary numbers and simplify. And it should read 5i. We're going to do that one together, and then I'll give you another. No, don't say it out loud. Let people think, please. Okay? 5i. Here we go. Let's do this one together. It says, square this number. What does that mean? Parentheses to the what? Second power. That is correct. How do we rewrite this? Like this, Mr. Q. 5i times 5i. Oh, Mr. Q, can we just distribute? Right now I want to see the work. Because people are going to get confused with the rules of exponents right now. But right now I just want to see the work. Next. Do we have multiplication all the way through? Yes, that means I can rewrite this as follows. 5 times 5 times I times I. Do you agree with that? Yes, that's called the commutative property of multiplication. So if this is true, what is 5 times 5? 25. What is I times I? I squared. And now we can do substitute and simplify. 25 times, what is I squared? Negative 1. That means this is negative 25. All right. Do this one by yourself. Do the entire process. Even though it's very similar, I just want to make sure you got the process. Let's do 9i. Square that and simplify. Copy that and go. I'll give you some time. All right. Check with me there. See what they got. Answer, negative 81. Hands if you got that. Okay, that is correct. Let's crank it up a notch. Example 4Q. I'll give you a head start for this one. It's the same process. It says square it, simplify it. Same process. I'm just building it up a little bit more. Now I'm including negatives, i's, and square roots. I'll give you some time. Copy and go. Here it goes. So the second power, negative I square root of 2, negative I square root of 2. We can rewrite it as negative I times negative I times square root of 2 times square root of 2. This is I squared. This is square root of 4. What is square root of 4? 2. What is this one? Negative 1. So therefore, negative 2. You're going to get some quadratic equations where you need to simplify at the end with some imaginary. See how you do with those. Have a good one, guys. Take care of home play. See you guys till Monday. Yes, and get those papers signed. That's due on Monday. Bye. Yep, the parte. Bye. Yeah, for those of you watching the video, tell your parents, parte signed, and your home play were those pages 122, page 122, and 123. That's home plate, yes. So we're on the board. Have a good one. Bye.